Hello, everyone. It's Larry Kotlikoff back with Economics Matters. We're going to talk today about something that's related to economics, physics. And I've got with me my dear longtime friend Larry Sulak, who has been instrumental at Boston University in developing physics and improving physics dramatically. We both joined Boston University around 1984, right, Larry?
Exactly.
And I became chair of the economics department. Our ranking went from 86 to 7th. And physics similarly made a meteoric improvement under Larry's leadership.
I joined the same year.
We joined this, yeah, so it's two Larrys. So Larry is one of the top physicists in the world.
You exaggerate.
He's he was born in West Virginia. I'm going to ask him to say a few words about his background and how he got into physics, and then talk about a little bit just about his career. But we basically want to talk about a discovery that he and other colleagues have jointly made, which is they found the fastest ever neutrino. A neutrino is a particle, and most of us, including myself, who are not really cognizant of what's going on in physics and really trained in physics, we're really ignorant about physics. We don't know that the world consists of little things, tiny little particles that are running through our bodies every instant. And one of the important such particles is our neutrinos, which took a long time, I guess, to discover. And he's going to explain how this was discovered and how you discover neutrinos and what it means to find the most, I guess, the fastest neutrino.
And the highest energy.
The highest
2,000 times higher than what you can make at the collider in Geneva.
So this is there is a accelerator collider that's sending around particles in underground in Geneva, Switzerland. It's called CERN. And Larry's been involved in that project for decades, really.
Since 1970.
With many of the experiments being, much of the equipment and design of the experiments being based on things that Larry developed with co-authors.
Well, some, yeah.
With some. And some are, well, he's very modest. And he now has with others, a project that's embedded underwater in the Mediterranean, detectors that are picking up neutrinos that are being sent from black holes. Is that it?
Well, active galactic nuclei, we think. We can point back to a half a degree, that's the size of the sun or the moon.
Yep.
And there is nothing known out there at that particular place. So we really don't know where they're coming from.
Where they're coming from, okay.
And since they can penetrate a light year of lead without being deviated, there's it's hard to imagine what they're coming from since they can go through anything.
Well, okay, so let's just start out with where you were born. Okay, you were born in West Virginia. Where in West Virginia? And tell people a little bit about your evolution into, how you got from there to here.
It's relevant in any way, but it's 49 hills. Got so many hills down there, you got to number them. Apple Pie Ridge B, Apple Pie Ridge A goes the other direction.
Yep.
And I grew up on a subsistence farm, one pig. My job were the chickens and the strawberries. And I became the strawberry champion of West Virginia. And I got bored with that. There must be something else to do. And my father's goal in life was to go to the only school we knew that existed. That was Carnegie Tech in those days. Yep. So I was supposed to realize my father's ambition.
And your father did what exactly?
He was a ham radio operator and eventually an air traffic controller. Before that, he could fix anything for anybody.
I get it. And your mom, what did she do?
She was a cook in the school.
I see.
Grade school.
So you went to Carnegie Tech?
Yes.
Which was located in West Virginia, where?
No, Pittsburgh.
Pittsburgh, Carnegie, okay. And
Carnegie Mellon.
Carnegie,
these days.
okay, Carnegie Mellon, okay, changed names, okay. So I'm not there for, I didn't realize that it changed names, but, okay, so we're Carnegie Mellon, and how do you get into physics?
Oh, in those days, we had
Guess
an
I'm gonna pull this
enlightened
a little bit here.
government and the National Science Foundation
Yep,
funded kids from anywhere that had a brain to go during the summer and do research somewhere. And
Okay.
I did that for 4 summers. From middle school on, I did everything possible to get out of the mines because I had 2 grandfathers killed in the mine associated with it and 1 uncle. So the goal of every mother there was to get their kid out of that environment.
uh-huh. So you took a,
So I took the National Science Foundation summer programs, and one of them went through Carnegie, and that's where I had the opportunity to join a group of researchers at Westinghouse Research Lab, Beulah Road.
Westinghouse, okay,
Yeah, and got into the semiconductor business and took home to West Virginia the boats of boron and phosphorus and such, and made my own transistors out behind the barn, as you may say.
so you said you got your first patent based on work that you did in your barn, right?
Yeah, and as a high school senior.
High school senior, oh, that's amazing.
Exponentially retrograded hybrid photodiode.
Okay. So you went to college at Carnegie? Or
Yeah,
not?
luckily because of that NSF program, a guy named Harvey Nathanson, who became the chief scientist for Northrop Grumman, was my mentor. And
Okay,
Harvey helped me enormously.
great. And then you went from there to get your PhD. Where was that?
Oh, Princeton.
To Princeton for the PhD.
I was
Okay.
very lucky there too. It's the right person at the right time, maybe, or just the right place. There I had 4 Nobel Prize winners as teachers.
Who were they?
And later,
Just-
Wigner, Cronin, Fitch, Hopfield, or even another one. But anyway, those 4,
What year did you start?
66 and
Mhm.
finished in 70.
So you were,
4 years for an experimental PhD. That was pretty good.
and you knew some of these other people like Feynman and Teller?
Feynman wasn't there, but Feynman was, when I went to give my talk on my thesis at Caltech, he was a kid, go read my paper on such and such. You got to do your library work.
I see. So
He was a tough bird.
Jeff Bird. And you've had so after grad school at Princeton, where do you go?
I went to Harvard and worked with another Nobel Prize winner eventually. That's Carlo Rubio.
Carlo Rubio, okay. And
And
then,
he took me to CERN, and that's where I got started the first year.
because he's the director of CERN.
He
He
became
the
of
director.
CERN, yes,
Okay.
after he
Tell-
discovered the W particle, namely
Uh-huh,
the carrier of the weak force.
okay. And then from Harvard, we come to BU, I forget, was it
No, I
Harvard,
went to
MIT?
Michigan because
Michigan? Okay,
I wanted to build the so-called proton decay detector, and Harvard didn't want to do it. Harold Shapiro, the new president of Michigan, offered me $1 million startup that we could use to wheedle out of the Department of Energy another million. So we had got $2 million.
yeah,
That wasn't enough. The cost initially that we estimated was 4 million, but if you got 2 million, you do everything you can to make it work, and we did.
cool. I'm just raising
And I'm going to
this.
tell you about some of that work here, if you have a moment.
Okay, yeah, we're gonna go right there.
Okay, my thought is the following. For the 5th graders, I have some of those over there, or the core curriculum here at Boston University. I have the pleasure of going through a brief history of particle discoveries.
That's great.
And
Let's do that.
And it's all around me. It's
So this is,
my
we're
museum here.
in Larry's museum, and I'm just gonna show everybody, but actually we have one of his grad students.
Ashwar, yeah, meet
Ashwar.
Ashwar. Get over there.
Ashwar, say hi, Ashwar.
Hello. One of our graduate students in the CMS.
You wanna just, well, I can do this.
LHC group.
Here's one of the exhibits, which is Ashwar. And but I want everybody to see what we're seeing, which is a room full of all kinds of fascinating things, including the periodic table here and a picture of Beth Sulak, Larry's lovely wife. And here's Larry again. And we have, this is a picture of what is underground now, under sea, right?
Yeah.
In the Mediterranean. This is a prototype model, right?
Well, that big sphere.
That big round.
This is a benzosphere. Well, look.
Oh, the sphere,
okay.
sphere, not the round picture.
No, this
Okay.
is the G-2 experiment.
Okay, so you and Eshwar go do a tour, okay, of everybody.
Well, you're going to come with us.
I'm coming along. but
Eshwar?
You
Okay,
guys
good.
point the camera to.
Okay, so
Okay, let's start the tour.
let's start over here because we're going to talk a lot about light and the fact that when something that's got an electric charge wiggles, it gives off light. And so if you start your image of what it means to be a particle, it was first these lines, namely that every atom has a characteristic set of lines. That's how helium was discovered on the sun because of its particular lines. Anyway.
And that discovery, just to be real quick.
Yeah.
That discovery is by shooting light through.
Just looking at the sun. And when you look at the sun, it's
Is it filtered somehow?
Well, no, it's missing. Let's see if we see one here. This chart does not have it, but normally if you look at the sun, you'd think you'd see a whole rainbow, but you don't. There's some very distinct lines.
So do you have something between you and the sun to detect?
The atmosphere of the sun.
Okay.
And the atmosphere of the sun is cool, and it absorbs the light from the sun that is given off by the helium. I mean, the sun is nothing more than something that eats.
So how do we see
hydrogen
these
to make
lines?
helium.
How do we see these lines?
Well, you make a spectroscope, a little
A scope of what is that?
a prism.
Prism.
So you have a prism that splits the light into lines, and so for instance, here's helium. Helium has those lines, and you'll see them colored here because they're emission lines. But when you look at the sun, you see a dark band at every one of those. And I can't remember who it was, but some early guy said, wow, there's got to be some atom, I'll call it helium because of the sun, that it has that characteristic.
So you're looking at a gas, light coming through the gas, through a prism, and then you see these lines, and now you know
So
this
the
is
gas
this
is
is
there.
the atomic structure. You have something about the atomic structure connecting these lines
Right.
with the atomic structure. Okay.
Here's what the connection is. It's called energy levels. So the light goes through the atmosphere. It hits a helium and shoots it up to higher state. And it sits there for a while and then re-emits that line of light. So you can see either the absorption of it or the re-emission. And from all of those, you got that table. Really quite remarkable. Anyway, from that, you understood that electrons were held together by some positive charge, the proton. We'll talk about that later. Many of them together making a nucleus, and around it is this beehive of electrons that are probabilistically someplace around it, but in distinct energy levels where you can shoot it up and have it come back down. You shoot it up by absorbing light, you see it, the light comes down.
And the shooting up and down makes for the lines.
Exactly. Very precise. Okay, so that tells you that there are electrons. And if you make yourself batteries to measure what the energies of these transitions are, you can add up a bunch of batteries and you can make yourself an electron beam. So if you see that green light there, that's the toaster. I got a toaster oven here shooting electrons with a little bit of high voltage. So it's 5,000, right now you can see 5 kilovolts. And so I can attract with plus those negative electrons to make a beam to hit this white stuff, which is nothing more than zinc. When zinc gets hit by an electron, it gives off that green light. So anyway, so you're making some zinc, you see the light, and then the guys who, Mr. Maxwell said, wow, that's amazing that you can play with electrons and it doesn't make any sense. the South Pole pushes to the left, the North Pole pushes to the right. So it is something that's inherently three-dimensional and totally mysterious until Maxwell figures out the equations that describe precisely what's going on.
So this is electromagnetism.
Electromagnetism.
Yeah.
So you got the magnet, you got the electrons.
This is
that's
1895 or something?
Exactly.
Okay.
So we got that. Well, so you got the electrons, you got a bunch of electrons. Say, for instance, if you have uranium, you've got 92 electrons going around 92 protons. Those protons are all in that little bunch in the center. It's very small. It's empty space. Here you got all the electrons going around, and about 1 part in 100,000th. 1 part in 100,000th is that little nucleus in there. Okay, what about that nucleus? Well, not only did they pick up these atoms from the spectra, but also from playing with the materials. And some of those materials were quite unusual according to Madame Curie. Namely, they gave off something unusual, just in the same sense that the atoms that are excited give off light.
Mhm.
If you get too many protons, 92, into something in the center, it falls apart. It's like a bag of marbles with some glue in it. And that bag of marbles with the glue in it, if you put too many marbles in there, one or some of them won't break out. It can't hold them together. Why? You got a bunch of 92 protons, all with plus charges. 92 plus charges in the same little space. 1 part in a millionth of the atom, that little space, and they push themselves apart because of mutual
That's why
repulsion.
we have the emission of radiation from.
Yeah,
This is a detector of radiation.
Yeah,
I think that's
this
a piece of
Geiger,
uranium.
Geiger
It's a
counter.
Geiger counter.
There's some uranium in here. There's uranium in you. There's thorium in you. We'll look at that in a moment. At 1 part per billion. 1 part of you in 10 to the 9th. Oh, I'm afraid of nuclear. Well, it's in you. And if you didn't have it, you wouldn't have mutations. And if you didn't have mutations, you wouldn't have evolution. And therefore, you wouldn't have you. You've got to have the radioactivity. But what is that radioactivity? What happens when too many protons decide they don't like being next to each other? Well, the problem is one that's pretty ubiquitous. I come from West Virginia, as you said. Newell, West Virginia is where I grew up. And this is my mother's collection of, that's where I ate my Wheaties each morning. And and you always wonder why I am the way I am. Okay, now, similarly, if you go camping, that glass keeps it away from you, but inside the wick, inside that mantle, you've got thorium. So if you see uranium, it falls apart. So does thorium. These guys around here all have too many protons for them to be stable. Well, there are some very good aspects of being radioactive.
So this is radioactive decay is what you're talking
You've
about.
got radioactive decay. Here's your smoke alarm. Everybody knows about smoke alarms. And if you just open it up, what's inside? It's a piece of americium-241. Well, we can go up here, americium, there it is. And what do you have? Goes off the scale. Can you see that?
Yeah.
So americium is just wonderful because it gives off alpha particles. Namely, what comes off whenever it feels it has too many in there is it gives off not a proton, but it gives off what's called an alpha particle, a helium nucleus. We were talking about helium up there. Helium's nucleus is 2 protons and 2 neutrons. And that is the stablest thing on Earth or on the universe. So helium is made in the sun. We talked about that. And it's super stable. And so it comes out of here. And if there's smoke around, it's stopped immediately on the smoke particle and sets off the alarm so that you don't have a fire in your house.
Okay.
Okay, now another very good example of this case radiation, but an antimatter. Here, you can say you've held antimatter in your hand. This, if you can read it right here, what does it say?
Says
Sodium.
sodium 22.
Sodium 22. Well, what about that? You can see it goes bananas.
Yeah.
Sodium 22. Now, what's so good about sodium 22? Well, probably your mother and sister and friends, girlfriends, probably will use sodium 22 in their life. You've got to find out whether you have breast cancer. Works also on prostate cancer, which I have. So what you do is just take some salt and you put the salt on what you're eating, and that salt, you're going to put sodium 22 rather than normal salt. And if you do that, that cancer loves salt. It eats it up, goes right to the tumor, and this sodium 22 decays in a very wonderful way. It is antimatter that it gives off, positrons. So a positron comes out of this salt. That positron immediately finds an electron. Electrons are everywhere, and it annihilates. Positron and electron, matter and antimatter make two photons, two pieces of light. So let's say I have breast cancer and I eat some sodium 22 salt. Bingo, 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 bingo. If I have a way of looking and going backwards to where those photons came from, I can see exactly where it is. And we can develop with the BU Medical School glasses for the physician to cut out just the bad stuff.
So this is
But
the
you know exactly-
MRI detector.
Well, it's called PET scanning.
PET scan.
PET,
Okay.
positron emission tomography.
Wow. And how does the detector actually detect?
Well, how does this
It
work?
was like the
I'm
guy.
going to show you in a moment because the detectors are all around here. This one right here is a scintillator, and we'll go to that right now. But before we go, I just wanted to remind you that antimatter is your friend. It will help you a lot. Another thing that's your friend are neutrons. Here you have a neutron detector. You were asking about detectors. This one happens to be filled with boron 10. Boron, you know about 20 mule team borax.
Right.
Anyway, if a neutron goes into this tube with a gas of boron 10 in it, it immediately gives you a signal out, just like that signal that we heard on the Geiger counter. Why do you need to know that? Well, people are afraid of radiation. I'm afraid of radiation too. So you go around your nuclear reactor and you can tell immediately whether the guys inside are doing something they shouldn't or not. So it's very simple to know whether or not neutrons are causing troubles. Now, just like the periodic chart allowed some easy synthesis of how all the atoms go together, same thing with a nuclei. Even though it's a million times smaller, here's the periodic chart for the nuclei. You start down here with hydrogen and helium, and you go all the way up to the uranium and thorium. I didn't mention thorium. Thorium is the radioactive material that's inside the mantle for your lamp. Okay, here is the periodic chart for nuclei. Now it's a big long line. So the way you see it is you start here and then you continue up here and then you continue up here and then you continue up here. Now that's the status of where we were at the time of the Manhattan Project. You had to understand all these things in order to make that.
And the table's telling us what exactly?
Oh, each one you look at, it will tell you. For instance, let's find uranium 92. You see 92 here?
Yep.
So this is all uranium. So uranium has a lot of uncles and sisters and brothers that are related to them. And some of them are radioactive, like the guys in yellow. And some of them are very important because they fission, namely they break up, they don't give off just light, a photon, or just an alpha particle, a helium. They break into daughters, and in that process give off a lot of neutrons. We just talked about that neutron counter. And when you take a big bag of protons and neutrons, a nucleus, and you give it another neutron coming in, it very often splits in two. And those two not only split, that they give off 4 or 5 more neutrons. And so the next one gives off 25 neutrons, and the next one 125. So you have a chain reaction that allows us to have a power plant that makes lots of heat, because you get a lot of photons coming out at the same time, as well as all of these daughter particles.
Okay, so so this table was built based on detection of the particles?
Every one of these is essentially a big dossier, somebody's life work in general. And I don't know how many people were at Manhattan Project. My thesis advisor, Val Fitch, was. So was Eugene Vigner, another one of my teachers. And I'm sure there are probably a couple thousand people, and each one was studying one of these to understand how it decayed and how you might use it or not. Not using it to absorb things. Some of them absorbs neutrons, and so very good. If you put boron into a reactor, it stops because boron loves to eat up the neutrons. On the other hand, if you put in uranium-235, that black guy right there, then you get fission and you get a lot of extra neutrons, and you can have an explosion.
So just going back to the Geiger counter,
Yeah.
just tell us a little bit about how that works again,
Oh, yeah.
because I want to make sure we.
Do I have something over here that I can explain better? No, I guess not. Let's just do it here.
Because so much
Here.
relates to detection, right?
Yes. Oh, yes. So this happens to be a scintillator, and we'll go and look at that again. But a tube like this is quite helpful. So this tube is empty. In it, you have a gas. Typically, it's for a Geiger counter, argon. And you have a high voltage. You can see that connector right there where you see the Teflon. That's where you can put typically 3,000 volts on that. So you put 3,000 volts on there. If a charged particle goes through, it ionizes the gas. What does that mean? That means you have this proton with a bunch of electrons going around it. And if a charged particle goes through, it knocks off one of the electrons.
Okay.
And that atom, which used to be neutral, now is charged. And if it's charged, it will make a spark if you have a high voltage on it. So essentially, you're making a little spark in this tube, in this noble gas. I didn't put it here, but you can see it. Oh, right, I can do it right now. So noble gases are those that don't suck up electrons. They're all full. So helium, neon, argon, krypton, xenon, all those guys have full shells of electrons. They don't rip out. There's nothing to pull off. So those guys, if you stick them in a tube like this, you can ionize them, but that is it. They won't eat the electron that you've knocked out. So a particle goes through. It makes typically 10 to the 7th, that's the multiplication factor. One charged particle through here makes 10 million little electrons along its path. And when it makes those charged particles, if you have a 2,000 volts on here, you make a little spark. And when you make that spark, you hear the result in the amplified Geiger counter.
Cool.
The other way of doing it, besides using a gas, is this. Here's a scintillation counter. Let me show you some scintillation counters over there. What they do, let's just take a slight detour over here.
Yep.
Here you see wonderful plastics. You've probably seen these before. And
Right.
Where are we? Yes, good. So what happens in this so-called scintillator is that if a charged particle goes through it, it rips off the electrons in its path, and that excites the dye that's in there. So it's a dye like any other dye in your clothes or whatever. It gets excited. So you've got the molecule, typically for scintillators. You got the molecule, you've excited it, it goes up to a higher energy state, and a little bit later, typically a few nanoseconds, that comes the excited electron comes back down and emits light. So right now you can say, well, why is this so light? Well, the particle is being stimulated by ultraviolet. These lamps up here give off a lot of ultraviolet light. So the ultraviolet light comes in, just like a charged particle. It excites an electron inside the dye. The electron a little bit later decays. And when it decays, it doesn't go from its ground state up. It stops halfway down at a metal stable state. And then it goes again. So it may give off the green light here or there. Oh, what are we doing? Are we already 50 minutes into this?
No, we're,
Yes.
but let's keep
That's all
going.
right?
Let's keep going. We're good.
Okay. So to collect this light, physicists do a lot of tricks to have the light from the scintillator go down into a phototube. Let me see. I have some phototubes up here. These are marvelous devices. It's the equivalent of the Geiger counter for charged particles, but it's for light. So if you want to see light, this is the inside of one of these tubes. You can see this beautiful amber color in the front.
Mhm.
That is sodium. So it's a vacuum tube, vacuum inside, sodium evaporated on the surface. And then the same old trick. You put a high voltage on this thing, but you put it on slowly. You put 200, 400, 600, etc. volts until you get to 2000. And it turns out that when a photon comes in to that sodium, and the sodium knocks off an electron from that sodium, it goes to the first stage. It's called a dynode. Then the second stage, and it multiplies each one. So 1 photon in, 1 volt out. Typically a gain of 10 to the 7th. It multiplies the signal, the light signal, by 10 million times. This is a miracle maker. And you have these on the end of your scintillators. So those are the two techniques. If you want to see light, you use this technique. If you want to see charged particles, then you use what looks like a Geiger counter, but a little more modern. Here are the Geiger counters that I used in 1970. This is with Valfrich and Cronin, 2 Nobel Prize winners from their work with these. So when a charged particle goes through this standard pile of aluminum, if it goes through like this, and you put the high voltage on it, and you have a noble gas in it, you get a spark, and you can trace the particle and see where it came from, measure its energy, measure its momentum, see what it came from. And in that process, there's another scintillator that's very good. It's called lead glass. If you have a fancy heirloom in your house, you may have something made out of lead glass. It's another material that luckily scintillates. Namely, a particle goes through, it gives off light, and you can put your phototube on the device and measure how much energy was deposited in that glass by seeing how big is the signal that comes out of the end. And you can measure its time too. So you can have 2 or 3 or 4 of these in a row and say, is the particle going at the speed of light, or is it slower, or what have you?
Cool.
Now, the modern version of the spark chambers is a multi-watt proportional chamber. That was invented by another friend. You can leave it down. This isn't that. Not important. I didn't realize it would fall out. Charpak. So if you look at this carefully, you'll see there are X and Y wires. They are quite special. If you are in the business, you are an aficionado of fine wires. These wires are typically 50 microns in size. That's about half the diameter of your hair. They're made out of tungsten so that they don't burn out being so thin. And they're coated with gold so that they have a nice uniform electric field. So what used to be done by the plates you see over here is now done by multi-wire proportional chambers. I use this for the first experiment to be published or to be done and published by yours truly in the Fermilab when it turned on. So what do you learn from these kinds of detectors? Well, if you take a look at the proton, just like everything else, but now your microscope has to be 1,000,000 times finer. And what that means is 1,000,000 times more energy. The energy and the distance are related by what's called the uncertainty principle. Let me turn this thing off. Okay, so if you do those experiments I'm mentioning, which take 40 years, you find that inside each atom, there is a nucleus. We talked about that. Each one has a proton. Here are 2 protons and 2 neutrons. That's that helium we talked about, the alpha particle. And if you look close enough with high enough energy so you can see the smallest particles, you'll see 2 up quarks and 1 down quark in this proton. And you'll see 2 down quarks and 1 up one in this neutron. And that's what gives us our best knowledge of the particle world, the smallest particles. Matters and forces. The matter is what's called fermions. Fermions are things that don't stick. They repel each other. They can't be in the same place at the same time with the same energy, whatever. So what do you have with these fermions? There's an electron. Everyone more or less has a feeling for a little point-like electron that's buzzing around like a bee around a hive. There is a heavy electron. It's called a muon. This is an obese brother of that electron's sister. That obese guy is 200 times heavier than the electron, and we have no idea why. We've tried every possible experiment. No one knows. And then even further, there's an even more obese lepton. It's an electron, a muon, and a tau lepton. Well, so we're wondering what they are or why they come in triplets. What you're going to find is everything at the sub-micron level, sub-micro level is coming in triplets. Anyway, associated with each of these leptons, the electron, is a neutrino. This symbol here is the Greek letter N for a neutrino. There's an electron neutrino.
So are these things all inside the atom?
Well, they come out.
They're coming out.
When you smash together 2 protons, out comes electrons, muons, taus, etc., because they're associated with the decay products. The decay products are here. Typically, when you smash a couple of protons together and observe everything with these scintillators and wire chambers, you see coming out pions, kaons, all kinds of particles. And all of these are short-lived, and they all decay eventually into essentially neutrinos, plus they're associated.
And you can tell these different things are coming out from these detectors. They can detect this is not that.
Oh, yes.
Yes.
Very precise. And in fact, this may be the time.
So this is how we just developed this entire kind of menagerie of particles by finding all the detections.
Right. At the time of the discovery of the Higgs boson, the big mystery of all this
The Higgs
discussing is
Higgs,
what gives mass to these things. If the muon is 200 times heavier than the electron, what's going on? Where did that mass come from? Well, the mystery is when we discovered the Higgs, that happened to be on July the 4th, 2012, we already knew
Oh my God.
So that's 60 years of making the observations that I'm talking about. 60 years by probably, there were, because I think I knew most of them, 1,500 physicists.
Wow.
And we were completely baffled, we still are, because we didn't understand why or where all this comes from, except for our colleague, Shelley Glashow, who has a so-called standard model of particle physics, and every number in this book fits Shelley's picture.
So
And
when you
Shelley's
say,
picture
yeah.
is this.
So Shelley's picture, Shelley Glashow, who's a Nobel Prize winner.
You
And a
should
colleague,
interview him too.
we should, and I will. Shelley is here at Boston University with us. Fantastic person and brilliant. And you're saying he put together a mathematical model that predicted all the numbers in this book.
Well, he doesn't predict them. Every number in this book, if you ask what it would be in his model, agrees with it.
Okay.
Well, how would you say it better, Ashwar?
Yeah.
I would say the important thing is he built the model after the data was collected, right?
Well, not after 60 years. He built the model in 1963, right?
Right.
Something like that. So since his model, nobody has made a measurement that contradicts it.
So is it fair to say that Shelley Glashow is the greatest physicist, or one of the greatest physicists ever? Let's put it that way.
Yeah.
Among the
What do you think, Ashwar?
Yeah, I would say so.
Okay, so we'll have to have him on for sure.
Okay.
So he had, and this was a mathematical model.
Oh, yes.
So we're talking
We're
about,
talking about the triplets.
okay,
So you got, look up here. We got the triplets of what's called heavy electrons. We got the triplets of neutrinos. The quarks, we talked about up and down quarks. Not only are there up and down quarks, there are strange quarks, which those chambers help discover. The charm quark, the top quark, the bottom quark, again, triplets. Triplets, 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 triplets.
can you give us a feeling for the mathematical model? I mean, we're talking about
That's
a
Ashwar's
model with, thousands of equations. We're thinking
Okay,
about-
Ashwar.
Are we
Now, how do you answer that question?
Are we thinking about a model with, a very, something that can, because we, in economics, we write down mathematical models and they don't go on for miles. They go on for pages, 30 pages, 40 pages. But what kind of model are we talking about mathematically speaking here?
Well, I don't know,
Okay.
but that is what a lot of people are working on right now.
Okay.
So, but I don't
What
know.
about Shelley's modeling, his mathematics?
It's very good, but I think there are certain discrepancies or certain inconsistencies are being discovered today.
Okay, so nothing's ever going to be, the end of the
Right.
the end of the story, but if we think about the amount of math that's involved, I mean,
It's enormous.
it's an enormous amount of mathematical equations that are underlying.
To check all this, every number in here is checked with great detail. With it, and a number is not physics. It has to have an error bar on it. So it's not only the number, but the uncertainty.
Right, okay. Yes. Okay, so, but we have, the beauty of physics and the beauty of economics is that a small set of equations, mathematical descriptions, can then generate a lot of prediction.
Yes, well,
And
that's
that's-
precisely what these
And that's what we're
triplets.
talking about happening here, right?
Yeah.
Right.
It's
We're not-
called, it's group
So-
theory. It's special unitary group, and in this case, SU3
So
plus
it's,
SU2 plus U1.
so it's very high-powered mathematics. Would we?
No,
would
it's
be a way
what
of-
Gene Wigner did when he was doing nuclear physics in the time of the
But
early
for somebody
50s.
taking high school algebra,
Oh,
this is miles beyond that.
yes.
Yes.
Well, Ashwar, what would you say?
It definitely is. Yeah.
Okay.
It's,
Okay, so we need basic science and we have right now, a policy of destroying basic science. We should point out in the middle of this, by undermining, grants to universities all around the country.
Well, let's go on as
But
to
let's move-
what
let's
else
continue.
is it that's useful around here. I'm going to give this back to
Who's this
Ashwar.
picture of anyway?
Oh, is it? Come on. All right, let's go on about
This is-
those neutrinos.
Let's make
Okay.
sure everybody sees that picture. That's a good picture of you, Larry.
That's ages ago. All right, let's talk about the neutrinos.
Yeah.
Because nobody understood the neutrinos. Fermilab was built.
Okay.
And first experiments
In
on
Chicago, right?
Yes,
Right.
right outside of Chicago. I had the pleasure, as I said, doing and reporting on the first experiment from there. But I
Is this
wanted
the
to
Argonne
do more.
lab?
No, Fermilab National
okay.
Laboratory. Yes,
Outside Chicago. Okay.
yes. There's another way of looking at neutrinos. When we say that particles come down and hit that Geiger counter all the time, you heard it going click, 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 even if it didn't have a hot source nearby. That's because cosmic rays are going through us all the time, making the mutations that give evolution, etc. And they can go through the Earth, a light year of lead, and so why not use the Earth as a shield, go down a kilometer deep, take a machine from Sweden with titanium boring on it, build yourself a 5-story hole. I have my pointer here somewhere. Where's my pointer? I can use this one. Okay. So here's a 5-story hole, 6 stories where we've got the top up here, we have the equipment, and you can line that hole in salt with a California Canal liner and fill it with water.
So we're going down a kilometer down into the ground and
Yes.
building this
This is
chamber.
underneath Lake Erie.
Like here.
Underneath Lake Erie. Okay, so this is the experiment I started in 1978. Its purpose was to fill that tank lined with this liner with water, the world's purest water. We could say, hey, Culligan man, and have him come and help us figure out how to make reverse osmosis water in big quantities. Because you see here, you've got 10,000 tons of water. And why did we get, how could we do that? We got a grant from the Navy so that the ships and that period in the Persian Gulf, the Navy ships needed to have pure water. There was no way of easily getting pure water. So we got a contract for developing high quantities of very pure water to put on the ships and down in our hole in the mine.
Oh, okay.
Now, we talked about phototubes. Here are typical.
So you're back to
phototubes.
mining. The West Virginians back to mining.
Yes, my mother
Okay.
was so distraught. I tried to escape mines and I went back into a mine. Okay,
Okay.
well, we dug them. This is our project today. We got this machine from Sweden. One of the problems was the phototubes I showed you all over there were all flat-faced tubes. You stick this down 60 feet in the water and it will implode because it's flat. So we had to get companies to try to make spherical tubes. And the other problem was this spherical tube cracked. We built the whole detector and they all started cracking. So we had to find out why. And it was because of that sodium salt thing. If you use sodium glass, water leaches into sodium and you get a stress relief and it cracks. So we had to develop had the companies develop a glass that would not have sodium in it.
So you put these things in, they cracked, and then you had to pull them out and put in something new.
Yeah, we had to replace all the 5-inch tubes with 8-inch tubes. So here are the 8-inch tubes.
But nobody could go down. We're talking about a kilometer down.
700 meters.
So you had to
down.
do this all remotely, right?
Oh, well, you have the string. We pull them up. We have
Strings, yeah.
have a reel that reels
Okay.
them up.
Okay.
Okay, even then we weren't getting enough signal to satisfy me. So I had to invent these wave shifting plates. We talked about the wave shifter. So the light comes in, you can see it's blue light. The blue light comes in, gets shifted to the green and goes into the phototube. And this enhances the area of the tube by a factor of 2, giving you twice as much signal.
So here
Okay.
we're trying to detect neutrinos.
Exactly. So what would happen?
And the idea of putting them inside the Earth is to slow them down? Is that the-
Shield it. No, you're
Yeah.
away from electrical noise, lightning, the radio signals,
You
anything.
don't want any interference.
Exactly.
And why did you think that only the neutrinos would come down in there?
Nothing else can penetrate. You can measure it. You do measurements at various levels. You go down the elevator, and at each level, you take your scintillators, the detectors like that on the elevator, and you find out that when you get down at the bottom of this mine,
The only
you're
thing
in
that
good
comes
enough
down
shape.
is
As
neutrinos.
You're right, exactly.
Got it. Okay.
Now, what do neutrinos do when they go through water? It turns out that it's just like a bow wave being pulled by a ship. A ship is moving faster than the speed of waves on the water, and you see that wave going behind it. A jet plane going faster than the speed of sound drags a sonic boom behind it. A charged particle, say a muon or electron or whatever, drags a blue wave of light. So the wave of light is what you want to see in the detector. And here are typical pictures of them. One of the first particles we saw coming through our cubic detector is this white line going up, and that is a neutrino coming from below. It had to go through all of the Earth to get there. Okay, and and
So it's coming from, it's not just coming from the top, it's coming from any part
everywhere,
of
all
anywhere.
directions.
All directions.
So
yeah.
you can look back and see the black hole at the center of our galaxy, because it's generally at minus 60 degrees as we turn around each day. The black hole is moving
So
like
are
that.
more coming from the black hole than from other places?
Well, that was one of the hypotheses. Do we see more neutrinos or any neutrinos from the black hole?
And what's the answer?
What do I want to say? I'd rather say what we were really looking for and what we found.
Okay, go
Okay.
ahead. Yeah.
The whole purpose of this was Shelley's theory. That theory that explains everything in this book can be expanded or extrapolated.
And huge book, heavy, very heavy. Tons of numbers. Shelley Glashow numbers. All correct.
Yeah.
Okay, that's amazing. It's beyond amazing.
Okay, so if you go from his theory, which is SU3 cross special unitary group in 3 dimensions, cross SU2, cross U1, if you go from that and expand it, it becomes SU5. And SU5 says that, Larry, if you look hard enough, you should see ashes to ashes, dust to dust. Now you go back to the light. Namely, protons all decay. At a long enough lifetime, we proved it was longer than 10 to the 33 years. A proton might decay into a positron, plus goes to plus, proton goes to positron, plus 2 photons. So
Why does it take so long to decay?
because it's so stable, we don't know it. What we were looking for was this. This was the best candidate we ever had of a back-to-back. Here's your proton. It decays into a positron one way and into a pi naught the other way. This meson that then decays into 2 photons.
And that's all predicted by Shelley's model.
The SU5 model, yes, but we never found it. Here it is. 2 rings is what we would have expected. This was the closest event we ever got. But in fact, it's not a positron in a pi naught, it's a muon in a pi naught. This particular ring is made by a muon.
So does this contradict his theory or?
Well, no, you have to wait. You have to look longer. So the very fact that we did not find it led to this detector, Super Kamiokande in Japan. Our detector, the DOE said, we want you to make a superconducting super collider. So maybe the Japanese will give us money to do that. So you should take all your toys, this detector that we ran for 10 years, take it all over and help them build their detector. And the reason why that could happen was this. We saw in 1987 the first neutrinos from outside of our world. Here is a circle made by an electron shower that comes from a supernova, supernova 1987A. There were 15 different neutrinos registered, bam, 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 and they all looked like this, and they're all consistent with coming from the Large Magellanic Cloud. So since this made a spectacular discovery, that got the Japanese the money to build Super Kamiokande. So we started out with that 10,000 tons to this, which is 60,000 tons.
Well,
Um,
and what's the wine doing?
well, it's just the super, they're
it's-
celebrating the supernova.
I see. I got it. Okay.
Okay, now, but in the meantime, since our detector works so well, we designed something even better, a cubic kilometer detector, kilometer by kilometer by kilometer. And we tried to do it with this prototype built here at Boston University, Boston University Electronics. Well, along came 1993. We had a budget crisis. We had to solve the budget deficit. And to solve the budget deficit, we would cut this project called Newman. We would cut the superconducting super collider, and we'd save lots of money, a few $1 million. And D. Allen Bromley was the president's science advisor at the time. And he said, Larry, take your toys and go to Europe. There's not going to be any basic science in this country for another 20 years, which turned out to be true. Anyway, so I did. In any case, we went to Europe. We laid the cable. This is the superconducting cable that you need to send power out to 3,000 of these in a cubic kilometer away. And that's what gave the discovery 6 weeks ago of the world's, in the same kind of pictures, fastest, highest energy neutrino ever.
So tell us about this detector that's so we have a detector in the Mediterranean, in the water, full of these guys, right?
Yeah.
Tell us a little bit about that.
Okay, we can take a
We have
look.
like another 5 minutes.
Yeah, well, before, if I can have a slight opening for two other things, because when we came here in 1984, like you did, it was a trifurcation for me. We could do the G-2 experiment. We'll talk about that in an instant, and we did. We could do macro, looking for monopoles. We did. We could do our fair share for the super collider, and we did. So Boston University had 3 major contributions to modern science in this era. You may say we were greedy, but no, we just wanted to take the technology we knew. So for instance, this Cherenkov angles that we were talking about. Well, you can do that if you have transparent lead. So we had to develop transparent lead, and that's using optical fibers. And that allowed us to build this ring of magnets at Brookhaven. All those things were built in our machine shop downstairs. And that proved, at least, that Shelley's theory about the muon, his theory tells you a lot about this muon thing here. It happens to be a little magnet, and it is precessing. And if you stick it in a big magnetic bottle, this accelerator, and let it go around and precess like a top going around, you can measure what that precession frequency is, which Boston University did at Brookhaven Lab. There's the machine up there, and found a deviation of a few standard deviations from Shelley's. So is it really true? We took that ring and moved it all the way to Fermilab. Here's the Boston University G-2 ring at Fermilab, measuring again to a factor of 10 or 20 better than done at Brookhaven. And this is the data from this will be finished in the end of this year or so.
Cool.
So major contribution. Now, when you say, well, what good is that? Well, you may know that people use MRI to fix their knees. because those little precessing protons, in this case, as opposed to muons, you have to measure them to 1 part in 10 million. You scan your knee and measure the magnetic field all around your knee to 1 part in 10 million. You can do that because we developed there the ability to measure around that ring the magnetic field to 1 part in 10 million to allow us to test Shelley's theory.
So,
So you can do PET scanning. Well, I want to tell you about that. Here are those optical fibers. You can see how small they are.
yeah,
We developed with the same identical technique, one of our spin-off companies called Photodetection Systems, that resolution. If you have a breast cancer of that 1/10 of a millimeter size, we have the best resolution for breast cancer of any scanner that exists.
well,
Coming out of that crazy work.
so this is so important to get across the economics of this.
That's where the economics
This is where the
comes in.
connection between basic science, which we are destroying as far at the moment, maybe this will get, changed, turn around, but this
Breast
is
scanning
making-
and MRI scanning your knee.
yeah, medicine.
Direct.
Yeah,
You have to wait. You have to wait. How long is it? Well, we started out with this stuff 40 years ago.
Yeah.
So if you don't invest over a 40-year period, no one's going to do it.
also, if you get going and you need another 10 years and you stop it, you've wasted all that money, right?
Well, that's what
A lot
happened
of-
with the super collider.
Yeah,
So in terms of the super collider, the contribution of Boston University, here is the detector called CMS, and CMS, 2 detectors independently, Atlas. BU has a group in both of them. And those guys discovered this thing that sticks things together, the Higgs boson. And again, a major contribution, for instance, of our machine shop, if you take a look here. Here is the concept of what we would build. The size of a human being is about that big. Here it is, one of our collaborators putting the optical fibers together, the same fibers you see over there. Here's me inspecting the readout of them. And the 96-wheeled truck it took to take it from the construction area to the experiment.
wow, look at all these wheels, unbelievable.
And
It's amazing.
you lower it down into the pit, 100 meters down, and here it is coming in, the BU detector.
Good. So let's talk about this super
Yeah,
fast
oh,
neutrino.
Yeah, okay.
Oh, we saw it a minute or two ago.
Yeah, oh, yeah, right here. So the same reconstruction is done here as you have over there. Let's see if we can easily pull this thing up. There it is. So here's the neutrino coming in. It's the muon from the neutrino. It hits each of these phototubes with its Cherenkov light. The size of the star tells you how much light was collected by that sphere, just like that one over there. And the afterglow you're seeing now is the light that's scattered around in it. So this happens to be the French team. You can see the Eiffel Tower. Here's analysis team number 2. Let's see it go. So the neutrino comes in, the muon from the neutrino, and you can again see the afterglow afterwards. And if you look from the top, looking down from the sea surface, let's look at that again. I have it going to the next. Let's go back. I wanted to see that one again if I could. It's not working. So let's look at the third group of analysis. Here comes along the muon. You can see the spheres lighting up. And in this case, the number of photons collected are given by the bubble size, and the timing of them is given in color with yellow initially and purple at the end. That's the world's.
And what was
Fine.
discovered in a few weeks ago was the
Yeah.
world's fastest
That's it.
neutrino.
Yes, it's
That's-
2,000 times energetic than anything at LHC.
Okay, so
It's the highest energy and the fastest, closest to the speed of light.
Well, so this knocked your socks off?
Of course.
Nobody expected this.
Oh, we designed that detector, the water detector up there precisely to see these things.
Because you thought, okay, it should happen.
1976, I wrote the proposal. And my proposal in 1976 was to make the water detector to see just this event.
So we're talking like a half a century
For me to
later.
realize my dream.
Mazel tov. Okay. Larry Sulak, one of the world's greatest physicists
Oh,
and one of the world's greatest people.
thank you.
So thank you so much.
Likewise.
Lifetime friend. Larry,
And
thanks,
thank you,
thanks
Ashwar.
much. Ashwar,
Yeah.
say thanks. Okay. I hope everybody enjoyed that. We'll be back again with Economics Matters and some other aspect of the real world. Thank you.
Bye-bye.